Yeah, the flow comes late, yeah. And the ones who come late have to sit at the front. I see us enfrente.
Okay. Muy bien, pues buenas tardes a todos. As we mentioned before on Monday, the Institute of Physics is celebrating its 80th anniversary. And as a part of the celebration of this anniversary, it is a real honor and pleasure to have here Helen Quinn. For those of you that were not present on Monday, I will give some information about the standing contribution and career of Helen Quinn. She was born in Melbourne, Australia, and received her PhD degree in physics from Stanford University. She worked as a postdoctoral researcher at the German synchrotron laboratory in Hamburg, Germany, and then spent several years at Harvard University before returning to California in 1977 to work at the SLAC National Accelerator Laboratory at Stanford, where she is now currently emeritus professor. Over a long and distinguished career, Helen Quinn made many major contributions to the field of theoretical particle physics and is regarded as a leader in the physics community. She served as a president of the American Physical Society in 2004. Together, some of the contributions that very well-known works, for example, one of them is together with Stephen Weinberg and Howard Georgi. They explained how the very different coupling strengths of weak electromagnetic and strong interactions can be unified at a single common strength at a very high energy scales, thus allowing a unified view of all these interactions. In what is considered his most recognized work, and that was presented on Monday, is what is called Péchet-Quinn symmetry, was developed together with Robert Péchet to solve the so-called strong problem of the Standard Model, which additionally led to the solution of this problem and also to the postulation of particle physics, the axiom that is now a primary candidate as a leading candidate for the particle dark matter problem. Professor Quinn was also a leader of the theoretical development related with the analysis of CP violation in beam meson decays. Her work played an important role in the development of the Babar collaboration at SLAC, which eventually confirmed the Kobayashi-Maskawa theory at the origin of CP and T violations of quark decays. She has also been engaged in education issues. She acted as a chair of the board of science education of the National Research Council and had served on a number of studies. She chaired what is called the NRC Study Committee that developed the framework for K-12 science education, which is currently guiding the development of multi-state standards of science education. Helen served at the request of the former president of Ecuador as member of the Comisión Gestora to help plan and guide the initial development of the National University Educations of Ecuador. Her impressive production and productivity in education and science comprise near 200 papers that have been cited more than 60,000 times. Professor Quinn's distinguished contributions to theoretical particle physics have been recognized by many different occasions and prizes. She received the Dirac Medal for the International Center of Theoretical Physics in Trieste, Italy, the Klein Medal for the University of Stockholm, and the Swedish National Academy of Science, the SLAC Prize for Theoretical Particle Physics from the American Physical Society, and the 2018 Benjamin Franklin for Physics from the Franklin Institute. And for her contributions in education, he was recognized by the 2016 Compton Medal from the American Institute of Physics. For all this, it's a real pleasure to have here Helen Quinn. Please.
Thank you very much. Thank you for the introduction, and good to see such a crowd of people here. I hope, today I'm not really talking about my work, I'm talking about some important history of physics and a little bit about how physics is done and why I see this particular piece of work. The subtitle, which you can't read on this slide, which says Dirac's Incredible Prediction and Its Consequences. Its consequences are a lot about how we do physics today. So I'm going to talk about that. And incredible because Dirac couldn't believe it. He made a prediction that he didn't even think was possible to make. And that's one of the interesting things about this story. So, but we have to start with what did he know and why did he do what he did? So we have to take ourselves back to physics in 1928. Right? In 1928, there were only two known particles, the electron and the proton. They hadn't yet figured out there was a neutron. They thought atoms had some number of protons and the equal number of electrons, and somehow some of the electrons lived in the nucleus and some of them lived outside it. And none of that was explainable by forces that you could understand. So the whole world that we call nuclear physics and the world that we call particle physics was only beginning to be understood in 1928. The neutron is a 1930-32 discovery. Nuclei, as I said, were thought to be composites of electrons and protons. But we did know about spin. We knew that electrons and protons both had half integer units in quantum units of angular momentum, whereas any angular momentum of one particle moving around another in quantum mechanics comes in integer units of angular momentum. Particles, very strangely, carried a half of an integer unit. And that was understood, and the mathematics of that was understood, but how that all fit together with how nuclei work was just beginning to be understood. Of course, this is critical to all of chemistry because half-integer particles obey an exclusion principle. You can't put two of them in the same state. And that's going to be important in our story today, too. So this is the context experimentally. Theoretically, yes, we had quantum mechanics, but we had non-relativistic quantum mechanics for the most part. The Schrödinger equation or the Heisenberg matrix equations for quantum mechanics were quantum mechanics without relativity. But relativity, by 1928, we had both special and general relativity, so the mathematics of Einstein's theories were known, but they didn't fit together very well with the mathematics of quantum mechanics. And that was the problem that was bothering Dirac. There was a relativistic particle equation, a field theory for spin 1 particles called the Klein-Gordon equation. I like very much that I have both a Dirac and a Klein medal because then I cover all of them, right? The Klein-Gordon equation was a relativistic wave equation, but it didn't have any way you could put in spin. As those of you who are physicists know, that equation is quadratic in energy and momentum. And putting quadratic, but the spin matrices of Pauli and the Heisenberg matrix approach to quantum mechanics is linear in energy. So this was where Dirac started. He said, I want to make a relativistic wave equation that's linear in energy because then I can use the matrix approach and put the spin matrices into it and understand particles with spin relativistically. So that was his problem, that was his question. Very good question. As I said on my talk before, the question is what leads you to the good ideas. And this was where he started. Now I want to tell you a little bit about Dirac as a person, because it's interesting and I think it affects the way he did physics. Dirac was a very shy, uncommunicative person. He really, I would say today or recently, they've changed the diagnosis, but if we talk about Asperger's syndrome, probably that was what Dirac had. But back then, he was just a strange, shy man, and he didn't really interact well with other people. He married Eugene Wigner's sister, probably because he met her when he was at events at Wigner's house with other physicists. He never went looking for the company of women. But so he had a wife, but he always referred to her as Wigner's sister, not as my wife. So this begins to give you a feel for the man. One more story. This is a story which Heisenberg told. So Dirac and Heisenberg went to Japan to meet with Yukawa, to go to a physics meeting that Yukawa was organizing. And of course, in those days, to go to Japan, you had to take a long journey on a ship. So Dirac and Heisenberg were traveling together on the ship, and as usual on the ship, after dinner, there was social time, and there was music, and there was dancing. And Heisenberg was dancing with the young women on the ship, and then he came back to sit with Dirac, and Dirac said to him, Heisenberg, why do you dance? and Heisenberg said, well, you know, when there are nice young women, it's a pleasure to dance. And Dirac said, but Heisenberg, how do you know before that the young women are nice? So again, a very shy person. In fact, when he heard he'd been given the Nobel Prize, he said, I don't want it. I don't want all the publicity. And his friend said, you know, you get a whole lot more publicity if you turn it down. So he agreed to accept it. So this is the picture of Dirac, a person who really worked by himself, who went off in his little corner to think about what he wanted to think about. And what he wanted to think about, I've already set the stage for you. So what did he come up with? Well, he wanted to come up with a mathematics for the relativistic equation. I've really said everything on this slide already. So his idea was, I'm going to factorize the Klein-Gordon equation or the Schrödinger equation to get a linear equation. Now, that doesn't work unless you introduce some new mathematics, because you all know it's p squared plus m squared, and the square root of a sum of squares is not a linear expression you can write, or the factors of the sum of squares are two different factors. So he needed to invent 4x4 matrices, the gamma matrices, to get an algebra in which he could write two factors that together gave two linear equations, together giving you the quadratic equation that we know and love. And he found he could do that, and he could also couple into this theory the electromagnetic field multiplied by one of these gamma matrices. So he could write a theory not only for a free electron, but for an electron coupled to the electromagnetic field, which of course the electron should be. So this was a great success, And immediately he could see there was something right about this equation, because one of the puzzles of the time was something called the gyromagnetic relationship. This factor, which is the relationship of the gyromagnetic properties of an electron or a proton to the classical value. And its classical value is E over 2m, but in fact it's twice that plus some higher order corrections. And this equation gave that correct result. So he knew he was on the right track. He wasn't going to throw away this idea because it had already had one big success. But it also had what appeared at first to be a very sick feature. It had an infinite tower of negative energy states. That means the bottom falls out in quantum mechanics. If you try to find the ground state of a state with an infinite tower of negative states, normally you've got a real problem. So here's where the exclusion principle comes in, because you can only put one particle in each state. So the idea was, okay, we can fix this negative energy disaster by filling up the negative energy. The lowest energy state of this system is the state with all the negative energy states full and all the positive energy states empty. Of course, it has an infinitely negative energy, but we just renormalize and call that the zero energy state and go from there, right? So that seemed like a good idea. Of course, to do that, you have to somehow deal with the fact that it's an infinitely bottomless pit and cut off the energies at some point. And you can cut them off at such a scale that it really is not going to affect anything. So let's not worry about that. Just put the cutoff in, and we've got a solution. We've got the lowest energy state, and we've got the photon that can come in and can kick an electron from one of those negative energy states to a positive energy state. And we've produced a pair of particles of opposite charge, because the hole in the negative energy C looks like the energy of a particle. We've got more energy than the negative energy state. That means we have a positive energy state with positive charge. Electron and proton were the only two known particles. The positive energy particle, which also has spin 1/2, must be the proton, no? So that was the interpretation that was offered. These negative energy particles had to be the proton. Now, Dirac was a mathematical physicist. He knew there was a symmetry between the positive and negative states. He knew they had the same mass, I'm sure. But he said it's the proton, and somehow the higher order corrections will fix that up. This is a completely wrong statement. There's no way he could have really believed this if he thought it through. But also, he could not believe that you could predict a particle that had never been seen just from the mathematics of the equation. And that's a prime point of change, right? All of a sudden, he's making a prediction, not a prediction of how can I explain phenomena that I've observed, but somewhat like Einstein, a prediction of phenomena that I haven't yet observed, but my equations tell me I must observe. Einstein did it with special and general relativity to explain contradictions in existing theory. So Dirac does it here. But he predicts a new kind of particle, because this answer is, in fact, not the right answer and doesn't work. And the mathematics also was evolving over this time. So I'm going to change the language to the language of field theory, in which case we don't have to worry about the negative energy C. The lowest energy state is the vacuum. The negative energy operators annihilate the vacuum, destroy everything. Nothing, the answer is 0. But they can also create the positive energy particles. So you have the particles, you get rid of the whole problem, but you still have the positive charges. And the mass problem becomes more and more obvious. The positive particle has the same mass as the negative particle. Still, Dirac didn't say, I'm predicting a new particle. He still kept trying, and everybody kept trying to make it be the proton. Until another disaster is recognized. The equation that couples the photon to an electron and a positron not only can produce pairs, but it can destroy an electron and a positron and make radiation, photons. But if the positive particle is the proton, it says an electron and a proton can annihilate and make photons. Well, if that were the case, hydrogen would not be stable, and we would not be here. So the idea that and it was Oppenheimer who saw this, and separately Tam, the idea that these particles could be protons is absolutely ruled out by the stability of hydrogen. So he had to say, it's a new particle. But look what he says. He says, if it exists, it would be an entirely new particle. He still wasn't ready to say, my equation predicts a new particle. And today, we as particle physicists do that all the time. So clearly, this equation is a transition in the way we think about mathematical physics. The idea that the mathematics can tell us we have to postulate particles that we haven't yet seen is something every particle physicist today is quite comfortable with. We do it all the time, right? But it took, we're now at 1931. We're 3 years after he's written the equation, and he's still saying, if it exists. But somebody was clever enough, whoops, sorry about the slide going 2 years down the road, but another 2 years later, by 1932, positrons were an observed fact. Anderson thought of an experiment. You have cosmic rays, they're coming in, we can see that they're charged if we put magnetic fields and make them curve. How can we see whether the cosmic rays have electrons and positrons? Well, we can see some of them curve the other way, but maybe they were going the other way. So we have to know which direction they're traveling to see that curving this way and curving that way means I have both positive and negative charges in the magnetic field. So I put an absorber, and the particles go right through the absorber, but they lose some energy. So the curvature of their tracks changes, and I can know which direction they were going. And this was Anderson's idea, so he put an absorber and he looked at cosmic rays, and he saw electrons, and he saw particles that behave just like electrons, except they have the opposite charge. So Dirac's particles were observed, and not so long after, antiprotons were also observed, once we had an accelerator that could produce them. So the theory was a great success phenomenologically, and it forms the basis of the way we think about particles today. So this is where we got with that equation. The mathematics and the symmetries of the mathematics forced a prediction. And as I said, theories today now are quite happy to predict new particles because they have symmetries, and the symmetries say those new particles should be there. And it's been a very successful strategy. Quite aside from antimatter, we had strange quarks. Those were predicted by observing, but then they sold another symmetry that told us there should be more quarks. And we have all the rest of the quarks. We have the W and Z bosons for the weak interactions. Many, many particles that we now have clearly verified their existence in the lab were predicted by the mathematics of our theories before we could look for them. And in fact, we needed the theory to tell us how to look for them. And that's the way theory and experiment work together, right? We each build on the other and get to more knowledge of the world. We have all of that. So we keep going down this road with no reluctance at all. We have supersymmetry, string theory, brains, and all of these things predict new particles and new phenomena, which we have yet to see. Why? Why haven't we thrown out the theories? Because we didn't see the particles? Because the predictions don't tell us, or sometimes do tell us, the scale at which we need to look at, and we don't have experiments that can look at the scale where these things exist. With supersymmetry, we hoped we could see them at CERN. So far, we haven't. Maybe we still will with higher intensities. With string theory, the scales are so high, we don't know how to build accelerators to get there. So it's really hard to make your progress. As I said, it goes with experiment and theory building. Theory tells us what to look for. Experiment tells us which of the possible answers is a good one. Let's go on. When we don't have an experiment, we have lots of possible answers and no way to decide which one is the right one. So we're in a little difficult situation right now with this story. But there's lots of interesting ideas, and actually, it's funny, I've been talking about how mathematics drove theory. Well, in this kind of work, also theory drives mathematics. Particle physics theory introduces new mathematics to be able to write the kinds of theories we think we want. And there's another two-way street between physics and mathematics that is also very interesting to explore. So, I also want to make another point. Antimatter isn't just a phenomena of fermions. You know, rho mesons and pi mesons have antiparticles too. Scalar particles, vector particles, they all have antiparticles. And why didn't we notice scalar antiparticles, that every plus charged scalar particle has a minus charged scalar particle in all of our theories? I think simply because the charged particles we knew at that time were fermions. And so we weren't exploring charged scalar theories at the point when Dirac wrote his equation. So we first discovered the phenomenon of antimatter for spin-1/2 particles, but in fact spin 1 and spin 0 particles also have this, that every charged particle has an opposite charged particle of the same mass, is not just a phenomenon of fermions. Okay, so now we know every type of particle has an antiparticle. An electron, a positron, a proton, an antiproton, a neutron, an antineutron. Neutrons, of course, are electrically neutral, but they're made of quarks, and the antineutron is made of antiquarks, and the quarks have charges. So there's antiparticles for all these things. And then Dirac's equation and most of the physics, the relativistic field theory that followed Dirac's equation, such as the theory of quantum electrodynamics, those theories have an exact symmetry between the laws of physics for the particles and the laws of physics for the antiparticles. And once we found that parity was broken in the weak interactions, turns out this exact symmetry is also broken, but in such a way that CP, the combination of the parity or mirror symmetry, and it's actually mirror symmetry plus a rotation, this combination is a symmetry of strong and weak interactions, or eventually we found it's not an exact symmetry, but it's almost. The laws of physics for matter and antimatter are very, very, very similar. And that leads us to another consequence. First of all, when matter meets antimatter, they can both disappear and give us radiation. Matter is not stable. Mass is not conserved. This is a big change in the laws of physics that comes from the discovery of antimatter. We have observed this happening in the labs and used it to create antimatter in labs, and we know very well it's true, so that's one of the consequences of Dirac's equation. In fact, we use positrons for specific experiments, such as positron emission topography, where we can look at structures in the brain using positron sources. There are many practical applications of knowing about antimatter, but it also brings us a big puzzle. The puzzle is, how come, if the laws of physics for matter are the same as the laws of physics for antimatter, how come there's all this matter around us and not very much antimatter? How do we live in a universe which is so asymmetric between matter and antimatter when the laws of physics are the same? What could possibly get us to such a situation? Well, there's really three kinds of answers. I guess I'm skipping a slide back and forth. So again, just wanting to back up and talk about Dirac for a moment, then we'll go forward about how do we understand the lack of antimatter in the universe. Right? Dirac changed the way we do physics. He made it possible for us to understand that the mathematics can guide us to predict particles, and then we go look for them. not only that we have to find mathematics to explain the particles we've already seen, but sometimes to explain the particles we've already seen, we find we need more particles and then go find them. It's been so successful, now we have to see whether it will continue to be successful in the future. We don't know. I guess I went backwards, didn't I? But the cosmological puzzle, I call it the mystery of the missing antimatter. The antimatter in our universe is much less than matter. Why? How did it happen that way? How did the universe get to be like that? Well, Pauli actually has a very interesting statement on this. I think this is very forward thinking of Pauli. Pauli said, I don't believe in the whole theory. Meaning, I don't believe in antimatter or this part of this theory. And this is actually 1932 after the discovery of positrons. So Pauli's saying, I know positrons exist, but I don't really think this theory is right. Why? Because it tells me that the asymmetry between matter and antimatter, he calls it positive and negative electricity, in the universe has to be explained, and the only explanation he could think of was, let's make it an initial condition. The universe just started out with different amounts of matter and antimatter. And he says, it does not satisfy me to shift this imbalance, asymmetry, to an asymmetry in the initial state. I mean, if I make up initial conditions for the state of the universe, you can't prove to me that the universe wasn't started 5 seconds ago. The initial conditions I have to postulate to have a universe that we're all sitting here thinking what we're thinking, having the history we think we have, etc., when the universe started 5 seconds ago, it's clearly ridiculous, right? We cannot put enough initial conditions to make that work. But there's no principle of physics that says it couldn't be so. So the idea of imposing initial conditions on the universe is not a comfortable idea for physics. And Pauli said, in order to understand the difference in the universe between matter and antimatter, given this theory, I have to impose an initial condition. And I don't like that. And I don't like it either. So, but in fact, today, we know it can't be so. We take our current best theory of the history of the universe. We have a period of inflation. At the end of the period of inflation, there's what we call the Big Bang is the end of that inflation period. And the universe reheats and dynamically produces all the matter and antimatter that's currently there, or that starts us out. The initial condition is physically generated after inflation. Whatever was there as an initial condition before inflation has been so diluted by an e to the 60th expansion of space that it's totally irrelevant. And all the matter and antimatter in the universe is generated after inflation and is generated according to the laws of physics, which are particularly strong interactions, essentially exactly symmetric. So we know the universe started with equal amounts of matter and antimatter. And now the puzzle comes, how did they get out of balance? Because when matter meets antimatter, it annihilates into radiation. If the universe were not cooling, the radiation could collide and recreate matter and antimatter. But as space expands and the universe cools, the radiation stretches in wavelength and therefore reduces in energy per photon, and the recreation of the matter and antimatter diminishes, and eventually all of the matter and all of the antimatter would disappear and we'd be in a universe with just radiation. Well, that's not what we see, so that's not what happened. Now, if you had just a little bit more matter than antimatter, then all of the matter and antimatter could annihilate, and the excess matter would be all the matter we have in the universe today. And that's the way it must have happened, right? And we know from experiment just how much extra antimatter we would need to have, extra matter over antimatter we would need to have to get a universe that looks like the one we have today. So that will be an important point. There's another possible answer, and that possible answer is equal amounts of matter and antimatter, And somehow processes in the universe sorted it out so that we live in a part of space where there's lots of matter, and somewhere else there's a region of space where there's lots of antimatter, and there's just multiple different regions in the universe. Some of them matter-dominated, some of them antimatter-dominated, but in some, now the word universe takes on two meanings, right? Universe meaning the universe which we can look at, and universe meaning whatever there is beyond that as well. In the universe that we can look at, we have strong evidence that it's matter all the way out, just by looking. I mean, if you had regions where matter is meeting antimatter at the surface between the matter region and the antimatter region, space isn't quite empty. So there's particles meeting antiparticles. Those walls would glow. And we could see them, people have calculated, out to roughly a third the size of the visible universe. And we don't see any such thing. And the notion that you could take a mixture, and with very little difference in the laws between the particles and the antiparticles, sort that mixture into very large regions that are matter-dominated and very large regions which are antimatter-dominated, is just totally improbable. You know, physicists never can say impossible if they're talking about these kinds of things. This improbable is so improbable that in the everyday language, it's impossible. Let me give you an example of a state which is perfectly possible, but highly improbable, and we all believe it's impossible, right? So the state of this room with all the air underneath this table, right? That's a perfectly possible physical state of the room. But you can walk in and out of this room for 1,000,000 years and never worry whether you're going to walk into the room and have no air except what's under the table, because it's highly improbable that in the random motion of the atoms in the room, they'll all collect under there. So when a physicist says highly improbable, they mean, for everyday language, impossible. Right? So this sorting really isn't possible. It's not a possible answer. So the only answer is somehow the matter and antimatter got out of balance. And to do that, Sakharov in 1967 told us we need 3 conditions in the laws of physics. First of all, obviously, if the difference between the amount of matter and the amount of antimatter is what we call the baryon number. The excess of matter over antimatter is a quantum number that we can calculate for any state. And we have to have, if we're going to go from equal to unequal, clearly and obviously there have to be processes that can change that number. Well, it turns out even if we take the standard model at very high temperatures, there are such processes. And so that condition is satisfied. That's the second one. The first one that I wrote there is no CP symmetry. The laws of physics for matter and antimatter have to be slightly different. Why? If the laws of physics are the same, for every process which increases the amount of matter over antimatter, there's a CP conjugate process, a reflection under this symmetry, that changes the amount of matter and increases antimatter. And if the symmetry were exact, those 2 processes would happen with the same rate. So even though some processes are increasing the amount of matter, other processes are increasing the amount of antimatter or decreasing it, and they stay in balance. So we have to have some processes that are asymmetric. And we have that in our equations. We have now discovered in the weak interactions processes which are different for matter and antimatter. These tiny differences in the laws of physics have to account for how the matter and antimatter got out of balance. And the final one of Sakharov's conditions is another technical detail, right? It has to be a situation where matter and antimatter are not in thermal equilibrium. Because if they have equal mass, then at a given temperature, if they're in thermal equilibrium, their populations will be equal. So there has to be some phase change, some particular period in the history of the universe when they got out of balance, and then after that time when they got out of balance, no possible return to thermal equilibrium, because the processes which can change baryon number have been suppressed in the laws of physics. So there we are. We've got 3 conditions. Our laws of physics fit those conditions, and we can calculate, right? So we look at, for the CP violations, we have to measure the CP violations, find how big they are, and then apply that to the history of the universe. We can have rate differences. We can have these states, which are flavored neutral particles. So a particle made out of an S quark and an anti-D, or a D quark and an anti-S, and we can find their mass eigenstates are not equal mixtures of those two things, but unequal mixtures. That's a violation of CP and the laws of physics. We have these 3 things, and all of them have now been seen. And this is a bit of a technical slide. I'll go through it very quickly. The CP violation actually takes all of the pieces we know in the physics today. It takes 3 generations of the standard model to have, in the quark decays, weak interactions, enough degrees of freedom to have violations of the symmetry between matter and antimatter. And we found that, and because of this technical fact, which you can read for yourself. It means nothing to you, forget it. You'll learn it someday. So Kobayashi and Moskwa gave us the 3-generation standard model. We measured the parameters in B decays. And we find how big the asymmetry in the laws of physics between matter and antimatter are by measuring experimentally. And then we say, okay, how could this asymmetry make a difference in the history of the universe? And we find it makes a difference at the time where the Higgs field gets its vacuum expectation value. Before that time, all the particles are massless, and the processes which can change baryon number have a reasonably high probability, and matter and antimatter is in thermal equilibrium. As the universe transitions to a condition where all the particles have mass, the baryon number changing processes are suppressed. So let's think of a bubble. Inside the bubble, which is expanding at the speed of light, is the universe as we know it today. And outside is the high temperature condition where all the particles are massless. And at the wall of the bubble, particles and antiparticles, as the bubble wall grows, particles and antiparticles move through that bubble wall. And if they move through at very slightly different rates, and our weak interaction asymmetry says they would go through at different rates, we'll get inside the bubble different amounts of matter and antimatter, because some of the antimatter is reflected, and outside they stay in equilibrium, so the imbalance keeps getting corrected, but inside the processes which can change the imbalance are suppressed, so it doesn't get corrected, it gets stuck, and we get a difference in the amount of matter and antimatter, and that looks like a good explanation. Now, trying to calculate how big an imbalance we get from that process is a very approximate calculation. We know how to do it, but not very well. But it turns out the answer is too small by about 10 orders of magnitude. So we didn't have to do the calculation very well to know that that answer doesn't work, right? So this is still the best option, that there is some CP violation, some asymmetry between matter and antimatter in the laws of physics, which at some time in the history of the universe caused the imbalance, which gives us matter but not antimatter in the universe today. But it's not the one we know. It means there's something else we don't yet know in the laws of physics about differences between matter and antimatter. We have lots of ideas what it might be. Maybe it's something to do with neutrinos. Maybe it's something to do with extra Higgs particles. It's an answer not yet known. But it must be there because we observe we live in a universe with more matter than antimatter by a huge fraction. Essentially, we can say a universe without antimatter. It's only produced in high energy collisions and then it annihilates very quickly. So this tells us our theories are not complete. We need to go further. We need to find something more in order to explain the universe as we see it. And that's it. I think it's fascinating that we know enough physics today to say the universe started with equal amounts of matter and antimatter. And we've got it now today with unequal amounts. And we know some processes that could do that, but they don't do enough. So we've got to find others, and we've got to extend our theory. So when I say it's too small, what do I mean? How do I know it's too small? Well, I know what imbalance is created. And then I also know that in the early universe, there's the radiation that came from the annihilations, and there's the matter that's left over after this process is done, all the annihilations have happened. And I know how much matter I need because I can model the history of the early universe, and depending on the ratio of photons to baryons, the chemistry and history, simple observation. The half-life of a free neutron is 10 minutes, right? If we change the history of the early universe by having different amounts of expansion because we have different amounts of matter, we get different ratios of protons to neutrons at the time the universe has cooled enough to make nuclei. And if there's too few neutrons around, we get different ratios of hydrogen to deuterium to barium to all the light nuclei which are produced in the early universe we can observe. And that tells us certain conditions on how much radiation there was compared to matter. And it tells us that the excess of matter over antimatter needed to be about 1 part in 10 to the 10th. And our theory gives us about 1 part in 10 to the 100. So we're up a creek. We need something new. So this again, it's fantastic today. I mean, when I was a student, saying things with such confidence about the history of the universe, saying things with such confidence about the production of nuclei in the early universe and making those calculations, we've done a lot of progress in terms of understanding the history of our universe, and yet we still don't understand. And yet we have things, every time we answer one question, we find the next question we can begin to address. We couldn't even begin to address the question before we'd done this. But now we can address the new question, and it tells us there's something more to learn and something more, some way we have to change our theories. And that's the nature of science, right? Every time we learn something more, yes, it answers questions, but also it reveals questions we hadn't even thought about. So, what are the possibilities? I said this quickly, but I want to stress it. We have to go beyond the standard model. We have to add new particles, new interactions, new processes that we haven't seen yet in order to explain the difference between matter and antimatter in the universe, and probably for some other reasons as well. But this is one of the reasons that we know clearly we're not at the end of the road. In my opinion, we'll probably never be at the end of the road because of what I just said. Every time we answer one question, we find another question we didn't even know existed. And we find something exciting to think about. And that's the joy of science, both the answers and the questions. And as I say, either way, the standard model is not complete. So that's all I have to tell you. I'm ready for your questions.
Thank you very much for this extraordinary talk. Please, questions, comments for this?
Yes, over here. Wait, pass the microphone that way and then. Wait for the microphone so other people can hear the question.
So in the beginning of the talk, you told us that Dirac thought about this in terms of negative energies. But then when the new theory came, we now speak of antiparticles as having positive energies, right?
Right. The antiparticles always had positive energy, because when you remove a negative energy particle, that takes a positive, right? To take the negative energy particle and kick it up to a positive energy state takes a positive energy.
Right.
And so you add energy and you get a particle plus an antiparticle. The particles always had positive energies. We filled all the energy states, and those are not particles, that's just the vacuum.
Right.
right?
So is
there
there a way-
never were negative energy particles in this theory, even when we were talking about holes in the negative. The filled negative energy C is the ground state. It doesn't have any particles in it.
Okay. So there is no way that one could still think, just I want to finish the question, but I think you already answered, that we cannot think of antiparticles as having negative energy.
No. No, they have positive energy. They gravitate positively, just like the particles.
Okay.
And in fact, we know that from equivalence principle experiments, that different kinds of matter, whatever mass they have, in fact, in any matter, there's a certain population of particles and antiparticles in that matter, and it's different in different elements. And so the equivalence principle would be destroyed if antiparticles had negative energies.
Well, very nice talk. What you said at the end was that the radiation was appeared to the annihilation between matter and antimatter. That's what
Yes.
radiation is. So it means that the matter and antimatter appear first, then radiation.
Well,
or what
not
is it?
not exactly, no.
No, that's what I wanted you.
Yeah, okay. So in this theory of inflation, there's a lot of energy happening as the universe is expanding exponentially rapidly. There's a lot of energy in basically the pressure that's causing the expansion. And at it's a complicated technical point, but why did the expansion stop? That energy, you can think of it as something rolling down the hill, and it got to the bottom of the hill and it oscillated, converted the energy of its rolling down the hill into some other. I mean, normally, if we're talking about a ball in a track, the energy it converts into is heat. So the universe gets very hot. And it's so hot, there's lots of every kind of radiation, not just photons, but gluons and weak interaction particles. Everything is bubbling away there, and there's radiation and particles and antiparticles in thermal equilibrium created as that expansion stops and what we call it the reheating of the universe. And so in that time, there was lots of everything. And the universe was hot and dense and opaque, right? Because it was full of charged particles. And then and nuclei weren't stable because the collisions were such high energy that they would break nuclei apart. In fact, at the very beginning, it was so hot and so dense that you couldn't tell whether quarks were essentially free because it was denser than the inside of a proton, right? And then it expands and cools, and we go through many phases. The phase at which the nuclei become stable is cool enough that nuclei don't blast themselves apart in collisions, is one phase we can investigate and look at to find about what was happening in the universe very early on. Later, there's the time when atoms form, and the universe becomes transparent to light, and we look at the light that comes from that time, and we call it 2.7 degree background radiation. So we can many stages of history of the universe, we can actually investigate experimentally by looking at what we see out there. And the further out we look, the further back in time we're looking, because whatever we're looking at took time to get from there to here. And so we can really reconstruct a lot of the history of the universe with experimental evidence to guide us. We go back even further than that. When we talk about the inflation and the reheating, that's more speculative. That's based on our theories, our best understandings of how particle physics works, and it makes perfect sense in those theories. And it's hard to answer certain questions without that inflationary period, but we cannot see direct evidence for inflation yet.
Thank you very much. Matthias?
Yes. Is there any way to absolutely experimentally ascertain that baryons and leptons are actually particles, what we see today, that electrons are particles and baryons are also particles instead of, for example, baryon being particles and electron being antiparticles, because they are somehow decoupled in our world.
Well, no, they're not. They interact very much with one another, right? Both of them carry electric charges, right? So these are just, particle and antiparticle are just names we give things, right? And we call the ones that we have all around, we call those particles. And then when we discovered there was another set, we called those antiparticles. But we produce those antiparticles in the lab, right? So we have seen both anti-electrons and antiprotons, and in fact anti-neutrons. Those are produced in laboratories today. And we know that, in fact, they've even produced anti-hydrogen, right? Made of an antiproton and an anti-electron. And we can look at it and say, yes, that matches our theory. It has exactly the same mass as, anti-hydrogen and hydrogen have the same spectrum of states. And they have except the anti-hydrogen, if it happens to meet some hydrogen, is going to disappear, or they're actually both going to disappear. And all of those things are processes we not only in our theories, but experimentally in the laboratory, we've looked at them. And we could choose to call all positive charged things particles and all negative charged things antiparticles, and that's just a name, right? But in the way the theories work, it makes more sense to classify the two sets. The one set, the stuff we have around us, and the other set, the stuff we produce in the lab but don't always have around us, and that's just labeling.
You mentioned about how we can know what the original imbalance between matter and antimatter is from the original density of photons and matter, and that's related to the neutron lifetime. But there is currently this puzzle with the neutron lifetime about different experiments, the experiments with beams.
That's a fine detail compared to the level I was talking about,
is it?
Right? Suppose we change the density of matter and antimatter greatly, then what would change is not the neutron lifetime, but what would change is the amount of time the universe has to expand before it cools enough to make nuclei. And so it's not, I'm just saying it had to cool fast enough that there were still lots of neutrons around. And what changes as we change the theory is how long it takes to cool.
Thank you.
Some other comments? Yes, please.
So thanks, Helen, for a really nice talk. You initially nicely summarized the Dirac's initial attempts to identify the antiparticle of electron as proton and the various phenomenological problems with it. So the Dirac equation basically predicts that the antiparticle should have the same mass as the particle.
Absolutely.
And by the time of Dirac's attempts to identify it with proton, the mass of proton and electron was already...
That's right.
So why didn't Dirac look at,
That's a very, it's not quite impossible to put ourselves in Dirac's head at that time. So I can only guess. And I can guess that for him, it was better to think that somehow he didn't understand something about his equations than to think that his equations predicted something that nobody had ever imagined happened, right? So although he must have known that his equation had this symmetry, because he was, after all, a very good mathematician, he preferred to fudge it and say, well, there's a positive charged particle, the only one we know is the proton, so this must be the proton, and I don't understand how the masses came out unequal, but something higher order has to fix that. Right? That's what he said. What he was thinking when he said that, how he could possibly think that higher order electromagnetic interactions could make the mass difference between the electron and the proton, I cannot imagine, and I don't think he could either. So I think he knew that he was fudging it. But that's only my opinion, and it could be that he had some deep thought in his mind that I can't even imagine. So,
but
This is the interesting thing about trying to reconstruct history. I mean, I can't even reconstruct the history of my own ideas. Once I've understood something, I can't imagine why I was so confused before I understood it, right? So how can I imagine what somebody was thinking while they were confused? It's really hard, because once we know the answer, it seems so obvious.
You know, I was just wondering, are you aware of any work where he tried to actually explain the difference between the masses? Or,
There are places where he wrote, right? The statement, this particle, if it exists, will be an entirely new part of, that's a letter he wrote, right? There are things, we have not only the published papers, but back then people actually wrote letters on paper. And so we have a lot of a history of physics in the letters that one scientist wrote to another. And so you can go so far from the record, but then you have to speculate. And when you have to know when you're speculating, right?
Any more questions, comments? Let me ask you something. You mentioned that there are many examples in which you have symmetries that you predict particles.
Yes.
Another example, and Dirac was involved in that, was the symmetry between electric charges and magnetic charges.
Yes.
That's another example. Supersymmetry is another one. There is a rule in which you can decide when is it a good prediction. Or
when is it a good idea and when is it not? Nature tells us that.
Only that.
Right? The mathematics can be very pretty and the theory can be wrong. Right? Or the mathematics can be a bit ugly because we haven't got it right yet, but the theory isn't fitting nature. So which one do we pick? We pick the nature, right? But when we don't have access to experiments that can differentiate, we can have many ideas. I mean, one of the things you have to do as a scientist is be able to hold competing ideas in your head till nature tells us which one is right, right? And you may have preference because you like the mathematics, or you like this, or you like that, but you have to know that the final arbiter is experiment. And so we work that way, right? We always have more theories than there are varieties of nature. That's the way we work. We like to speculate. We like to expand and extend our theories and find new ideas that might be right. But how do we decide which one is right? The only way we really can in the end is experiment. And we get cleverer and cleverer about doing both direct experiments and interpreting information out of the history of the universe, which of course did lots of experiments for us, except they weren't very controlled experiments, so we have to be very clever to find out what the history of the universe is telling us about the laws of physics.
There is another question.
Well, it's not really a question, but a remark. Your talk was very enjoyable. But for the audience, I want to stress that the Dirac equation is not all history. It's been brought back
Absolutely
into focus by these extraordinary experiments done with Bose-Einstein condensates, with trapped ions, which are simulating the Dirac equation and learning a lot about it. That is new. It's very recent work, and so for the audience, it should be taken as a new era for the Dirac equation.
Thank you.
Graphene is another example. The graphene, I mean, is
Yes, I mean, advances in the laboratory both explore and expand our understanding of the theory we have already and prompt us to build new theory. And both are critical and important. And what is amazing is that in 1928, Dirac could write an equation which is still of interest today, right? That's the beauty of physics. Physics is universal and in some sense eternal. Once we've understood something like the Dirac equation, it's a property of humanity and we can use it and explore it further.
Any more questions, comments? If not, before we finish, I commented at the beginning that Helen Quinn got many prizes, many medals, but we believe that she deserves a new medal. And it's for me a pleasure to, to present you with the medal from the 80 years of the Institute of Physics.
Oh, thank you so much. And it's very pretty, too. Your microphone and my microphone don't like being close to one another.
Sorry. That's what you want to say.
Well, I was not expecting this, and it's a very beautiful medal, and congratulations to the Institute on 18 years of doing physics, and hopefully many more.
Okay, thank you very much.